Year 11, end of week 3 checkup or progress check. If you've had a bit of trouble with that, you'd like to go through that with me. A cyclist accelerates from 5 meters per second to 8 meters a second in 15 seconds. So when you're doing these linear motion or any motion problems, it's always a good idea to do a diagram. At the moment, they're not very complicated, but later on they will get more complicated. So it's always a good idea. So here he is at 5 meters a second. He's going to accelerate to 8 meters a second, and he's going to do that over 15 seconds. So we've written down all the things. Remember, u is your initial velocity. U comes before v in the alphabet. That's how I remember it. So it's initial velocity, that's final velocity. So he starts at 5, he goes to 8, it takes 15 seconds. What's the acceleration? V equals u plus at, or the other form of that is a equals v minus u over t, which is the change in velocity, really, delta v over t. That's another form. It's the same formula, it's just in a different format. Right, and you work that out. 0.2 meters per second squared. Determine how fast the cyclist travelled while accelerating. You've got two options. You can use the formula S equals ut plus a half at squared. S is the displacement. Or v squared equals u squared plus 2as. When I'm trying to choose, I try to choose one that doesn't rely on something that I've just calculated, but the thing that I've just calculated is acceleration, and it's in both formulas, so it's really not going to make any difference which one you use. I think this one's probably a little bit simpler in its format, but it's not going to matter. Choose either one of those because you've got u, you've got t, and you've got a, so you can find s, or you've got v, u, and a, and you can find s. So that's not a problem. And you find it's 97.5 meters. Now the question asks for distance or how far, so you don't need to put in any kind of direction with that. It's just a straight out distance, 97.5. Next one. Driver traveling at 10 meters a second, and look, here's my little diagram. He's going 10 meters a second, sees a child run onto the road 10 meters in front. It takes him 0.2 seconds to respond. That's his reaction time. And the maximum braking acceleration of the car is -8 meters per second squared. Righto, so the negative is going to indicate that it's slowing down. Draw the graph. So I've actually put some divisions on my scales here because from the story that's given to me, I can be a little bit more precise than just doing a general shape. So for the 0.2 of a second in his reaction time, he's going to keep going at 10 meters a second. Then he applies the brakes at 8 meters a second squared. So in the following second, so by 1.2, his velocity is decreased by 8. So he's decreased 8 meters per second in 1 second. So I can get the slope on that line correct. And then I didn't have a ruler because I was slack. You just extend that line then until it hits the axis there. All right, so that would be my sketch of the story of the situation. Calculate how far the car travels before he applies the brake. Well, that's just going to be 10 meters a second for 0.2 seconds. So he's going to go 2 meters. Determine the time taken to come to a stop, his braking time. Now, come to a stop, that means that here, v, his final velocity is 0. He's starting at 10, 10, 0. Acceleration we know is -8, and we want the time. I'm going to use that formula there to find that the time is 1.25 seconds. Calculate the stopping distance. So the stopping distance is made up of the reaction distance and the braking distance. We've already worked out the reaction distance was 2 meters earlier. So we need the braking distance. So when he's finished braking, his final velocity is 0. He started from 10, that's initial. We know the acceleration is -8, and we want the distance, we want s. So it works out to be 6.25. So the total distance is the reaction distance, which was 2, plus the braking, 6.25, 8.25 metres. So he is not going to hit the child, which is comforting. Question 3. This was a revision type question. It's a little bit of a tricky one in that we've got a change of state in the middle of it. So 380 kilojoules of heat is used to transform solid ice at -12 to liquid water at 56 degrees Celsius. Calculate the mass of ice transformed. So the amount of heat that's given to it is used to heat the ice up from -12 to 0. It melts that ice and then it heats the water from 0 to 56. So there's 3 components to it, 3 stages. The mass is going to stay the same. That's what we're looking for. The mass is the same in all of these, so we can just leave M as it is. So that the amount of heat that's used is going to be MC delta T for the ice, M times the latent heat of fusion for ice, and then MC delta T for the water. So we just leave the M. We've got M equals, that's the specific heat capacity of ice. That's our temperature change because it went from -12 to 0, so it'll be 0 minus -12. That's the latent heat of fusion. And these figures just come out of tables. If you're asked to do a question with those, there'll be tables that have those values in them. And then this is heating up the water. 4,180 is the specific heat of water. And it goes from 0, that's the final temperature, 56. So it's 56 minus 0. Put that all in, work it all out. We know Q, they told us, was 380 kilojoules. So it's 380 by 10 to the 3 joules. Do your division. The mass of ice is 0.64 kgs.